Okay, for Chapter 16, we're going to try something a little bit different. As we can see here, Chapter 16, what we're dealing with is what's called energetics, or thermochemistry. So we're going to look at heat and temperature some more, the specific heat of substances, enthalpies of reactions, so the energy involved in reactions, the stability of those reactions, some combustion, and then some calculations here. So if we look, we've talked about temperature before. We need to state the units, do some calculations, all that. Let's get to it here. So in virtually every chemical reaction that we have, in virtually every chemical reaction, we're going to have a change in energy. Either energy is going to be absorbed or energy is going to be released. Now, if you remember from before, it's absorbed, we call that an endothermic reaction. So endothermic, and if it's released, it's called exo. Think of exo as exiting, exothermic. And really what these words just mean is really exiting heat and entering heat, endothermic, exothermic. So thermochemistry, really we're just studying the transfer of this energy in a chemical reaction. Okay, normally when we do these types of reactions, we use a tool called a calorimeter. We're going to use some basic calorimeters in our lab experience. The normal kind that we're going to use, or that you might enter in a college chemistry lab, is a bomb calorimeter, where we have some reactants that are in a reaction chamber that's immersed in water. As that reaction proceeds, it heats up the water. We measure the temperature change in the water, and that gives us the energy that's given off by the chemical reaction. Okay, so temperature, as hopefully you remember from before, temperature is equal to the average kinetic energy, or at least, let's say this. I don't like using the equal sign. There's a lot of weight that carries, but temperature is definitely proportional to the kinetic energy, and it's really a measure of the average kinetic energy of a system. That is what temperature is measuring. So remember, when we're talking about thermal chemistry, and we're talking about temperature, and we're talking about energy, we are talking about the motion of the particles. And the hotter a sample is, the greater kinetic energy it has. So the more temperature, the greater kinetic energy. And that means what? Well, that means the velocity of the particles. So really we're talking about particle velocity and how that's transferred in chemical reactions. Also remember, just like when we were using gas laws, is we always relate temperatures to Kelvin. So we will have to add 273 to our Celsius temperatures. The units we're going to use when we're measuring heat is the units called joules, and we'll define them here in a moment. So joules is the unit of energy that we're going to be using. Heat, when we use the word heat can be thought of as that transfer of energy. So heat, if we talk about the heat of a system, it is really thought of as the transfer of the energy. So when that energy is transferred between samples, that is the heat. A very important thing to remember based on thermodynamics is heat always will move spontaneously from the higher temperature area to the lower temperature area. So if we have two samples that are in contact, they have to be in contact, and one's at a higher temperature and one's at a lower temperature. Well, those two things, if they're in contact, they will equilibrate. And we know this. You know, if you take a can of Coke out of the fridge, you put it on the counter, it's going to eventually come to the room temperature. Well, and actually the room has slightly cooled because of that colder Coke, but so it does come to equilibrium. Obviously there's a lot more mass of air in the room than there is in that Coke can, so it doesn't cool off the whole room. Potentially, if you had a very large can of Coke in your house, you could use it to cool your house, or nobody would want to cool their house. Maybe a big warm cup of coffee at this point. Regardless, though, things are going to come to thermal equilibrium. So speaking of thermodynamics, here we have the most basic overview of thermodynamics that we could possibly get. So our first law of thermodynamics is that when we're in these chemical reactions, that energy is going to be conserved. It can be converted between forms, but energy is going to be conserved. So overall in chemical reaction, we have to remember the first law of thermodynamics, energy is going to be conserved. The second law, which is what we were just talking about, is that energy will flow and temperatures will equilibrate when they're in contact. And those are the two we're most concerned of. We can talk about the driving force for reactions as we get a little bit further here. So specific heat is one that's a little bit different here. Specific heat is a unique physical property for every substance. And what a specific heat is, it is telling us how much energy is needed to raise a temperature of a sample, a degree typically, 1 degree Celsius. So how much energy is required to raise a certain mass, a certain amount of temperature. So it's going to be a lot easier if we look at the. Okay, so the units of this are joules, like it says here, per gram, per degree Kelvin. Now notice, because 1 degree change, so if we have a 1 degree change in Kelvin, that's going to equal 1 degree change in Celsius. So these are sometimes used interchangeably. More correct, it's joules per gram per degree Kelvin. But let's look at what that is. Let's throw in a sample value. Say we had 50 joules of energy per gram per degree Kelvin. Well, what that's telling us is that it takes 50 joules of energy to raise 1 gram of the sample 1 degree Celsius. So let's look at a table of values of different materials to compare them. So here we have a table of values. Notice they have specific heats for each of these values in joules per degree Kelvin now these ones are per mole as opposed to per gram. We can use them either way. Typically we use per gram, but in these ones they're per mole. That's just what they are. That's fine. So notice we have things like aluminum as a solid, 24 joules, 24.2 joules to raise 1 mole of the substance 1 degree Kelvin. Now let's compare that particularly to water. If we go over and we look at water in its liquid form, its specific heat. Now water is a very small light molecule compared to argon or aluminum or iron or mercury. Those are all very heavy. Silver is very heavy. Notice water has a specific heat that's 3 times any of these elements. The reason, again, water, you can probably guess why it has such a high specific heat, is in one reason due to its high polarity and ability to stick together. So you notice there's not a lot of things that are on the same high level as water. We have to get into things like liquid octane to get up to levels that exceed that of water. The barium chloride as a solid has a specific heat that's as high as the molar volume for water. But especially most of our metals have really low specific heats in reference to water. And actually we know that, right? This is the rate at which things heat up. Joules per degree Celsius per mole. So if you go to the beach on a hot day and you walk across the sand is hot because the sand has a relatively low specific heat, so it heats up really fast. It doesn't take many joules to raise a gram of sand 1 degree Celsius or 1 degree Kelvin. Then you walk down to the water and the water can be cold. Well, the reason the water is cold again is because it has a much higher specific heat. It takes a lot more energy to raise the temperature of that water. So long last, here's our equation for specific heat. Specific heat is the heat on top divided by the mass and the change in temperature of that mass. So if we can measure how much heat goes into the sample, divide that by the mass of the sample we have, and how much the temperature has changed, to heat it up that amount, we get a specific heat. Now normally we actually don't use our equation this way, we flip it around, and often we want to solve for heat because our specific heats tend to be experimentally derived values that we use as knowns. So what we will have is we'll be calculating for the Q, the heat that's given off, or the heat that's absorbed, based on the mass of a substance, how much its temperature has changed, and its specific heat from literature. So notice as listed the givens, we put those in the calculator, just like I said, and notice what we get. And watch the units. Notice joules is on top, grams, and degree Kelvin on the bottom. So we have to still be watching our units always to make sure we're solving the problem correctly and everything goes in the right place. The next part of the question, in part B, and we didn't read it together, said, well, what would the Q be? How much heat would be required then to make this temperature change, to raise it from 314, raise it another 30 degrees Kelvin? Well, what we do is we take our same equation, but now we're solving for the Q. So it's Q, and again, I'm going to write capital Q just because I can't help myself, times C times delta T. So notice we have, in this instance, our C, that goes in here. We have our new temperature change, that goes here, and we have the mass of the sample. We assume it's the same mass of the sample, that goes here. So here's how the change in enthalpy is calculated. You take the enthalpy value of the products, you subtract the enthalpy value of the reactants, and the difference between them will tell us what our change in enthalpy is. So like we said before, one that releases energy is exothermic. So notice hydrogen reacting with oxygen. If you ignite hydrogen gas, and we've done this in lab, gives that little pop sound because it's reacting with oxygen, forming water. Well, that also releases heat. So it releases heat energy. So if we drew a little graph for this, hydrogen and oxygen would be reacting, and their overall heat would decrease when they form water. So what happened is, if this is energy, well, then a certain amount of energy was released. So they started at a higher temperature or higher energy level. They finished at a lower energy level. So heat was released, in this case, 483.6 kilojoules. What we would call this is, because the products have less heat than the reactants, this is going to be a negative change in enthalpy. And these energy values, well, they're proportional. So what that means is, if we increase the amount of water that's reacting in that prior reaction, we're going to increase the amount of heat that comes out. In an endothermic reaction, like if we wanted to take that water and put it through electrolysis and split it into hydrogen gas and oxygen gas, well, that requires energy. We have to put heat into the reaction. So it requires energy. We can actually think of the energy as a reactant. I like to think of the energy as a reactant, and in the former, we think of it as a product. So this would be an endothermic reaction because heat is required for the reaction to occur. Our heat is a reactant. Now, water is down here on our energy diagram, and our products are actually at a higher energy because we had to put heat in to form them. So we added heat, so we're going to have a positive change in enthalpy. So endothermic reactions, positive change in enthalpy. Exothermic reactions, negative changes in enthalpy. Okay, and like this says, and just like we were saying, typically, we're not going to write those thermochemical reactions with that value in. Instead, we're going to write them as a change in enthalpy, it being either positive or negative. Negative if it's exothermic, because the reaction is losing energy, energy is going out. And we would have a graph similar to this. And this is just what I said on our reactants. In this one, we had hydrogen gas, we had oxygen gas. They were at a higher energy state. The product, water, was at a lower energy state. This is the amount of energy that we could measure that's being released. And we could calculate it as well. We could take the enthalpy, again, of the products minus the enthalpy of the reactants, RXT for reactants, and what we would find is a negative change in enthalpy because it is an exothermic reaction. In endothermic reaction, we're going to see the opposite. The overall energy, the energy is going to increase because we're putting energy into the reaction. We're going to have that positive change in enthalpy. Okay, a few other things here. A molar enthalpy of formation that we might run into occasionally is the amount of energy or the amount of enthalpy when a certain compound is formed from its elements at their standard state. So if we form a compound from its elements at the standard state at 25 degrees and 1 atmosphere, that is going to be called the enthalpy of formation. And notice they have this little symbol here, meaning that it's at standard state. The little F is for formation. So that little 0 on top is from standard state, the change in enthalpy of formation. So an example is if you had sodium metal at standard state, 25 degrees, 1 atmosphere, it would be a solid. Reacting that with the element chlorine, which is a gas at standard state, to form sodium chloride, which is a solid at standard state, we could calculate the change in enthalpy of formation for that reaction. So it's forming a compound from its elements in their standard states. Okay, so we can look these up in a table. Normally, these things are going to be standards that we're going to reference. We can also derive some as well. One thing that we want to remember when we're doing enthalpies of formation is that if we have elements in their standard state, we're assuming the enthalpy of formation of those is 0. So what we're going to be able to do is we're going to be able to calculate overall reactions based upon the enthalpies of formation of individual compounds or elements that are in the reaction. Notice a few things that it says here is that compounds with a very large negative enthalpy are very stable. So the larger the negative enthalpy, the more stable the compound is, the more energy that comes off when it's made. Because then again, if we're making carbon dioxide from carbon and oxygen to make carbon dioxide, and there's a big negative number, that means a lot of energy is released. So our products are at a much lower energy state than our reactants. And lower energy states are inherently more stable. So if we go back to thinking about that energy graph, if our reactants are up here, our products are down here, and our products are at a lower energy state things are more stable. Okay, compounds with positive values are typically, they're less stable. So hydrogen iodide here has a positive value. And that means you have to put in energy to form hydrogen iodide. Hydrogen and iodide do not spontaneously react to form hydrogen iodide. So if we have hydrogen gas, we have iodine gas, they will not spontaneously react to form hydrogen iodide. We have to add some energy. That makes it a less stable compound. And notice, like it says here, it will actually decompose at room temperature into hydrogen and iodine vapor. We can also have some values called enthalpies of combustion, which, just like it sounds, is, and like the symbol shows, is the change in enthalpy when we combust or burn something. And normally, again, these are per 1 mole of product. So we have changes of enthalpy of combustion per 1 mole of product. Now, like our podcast started out saying, is a lot of these values, enthalpies of formations, and especially enthalpies of combustion, can be determined in what's called a bomb calorimeter. So we have a big sealed container. There's water around it. What we're doing is we're measuring the temperature change of the water. So there might be a sample in here. We have ignition wires, basically running an electric spark to ignite whatever the sample is. When it burns in here, it's going to give off energy to the surrounding water. We assume no energy escapes out of the bomb. The temperature goes up, and we can measure the enthalpy of that combustion. Okay, finally, this is where thermochemistry starts to get fun, is that what we can do is we can use Hess's law. And what Hess's law tells us is that the overall enthalpy change for a chemical reaction, so if we have a bigger chemical reaction, say we have sodium chloride, I don't know, reacting with something else, sodium or silver nitrate to give us, silver chloride, and sodium nitrate, say we have something crazy like this, well, we might not know the overall enthalpy of this reaction, but if we know the enthalpies of formation of each of the things in the reaction, we can calculate the overall energy change of the reaction. So the overall enthalpy change in any chemical reaction has to be equal to the sum of the individual enthalpy changes of all the individual steps in the process. So if we can sum up all those enthalpies of formation or sum up all the enthalpies of combustion, we can get the enthalpy of the overall reaction. And it's really crazy. It seems kind of crazy, but it does work. And it works on the basis of the conservation of energy. So if there's a certain amount of energy that goes into making sodium chloride, that amount of energy is a constant. And if that sodium chloride reacts with anything, that energy has to go somewhere or do something. So we're going to walk through an example problem on this. And what it says, again, just like we said, is that if we know the individual enthalpy changes of all the individual compounds or elements in a reaction, then we can determine the overall enthalpy without having to measure it directly. And this can get you around having to measure things directly that are very difficult to measure. So here's an example of Hess's law. We have the enthalpy of formation of methane gas from carbon and hydrogen. We want to get a certain value there. So we don't have it, but here are the things that we can pick out of our table. We have carbon reacting with oxygen to make carbon dioxide. There's an enthalpy of combustion there. Hydrogen gas burning in the presence of oxygen to make water. And notice this might be something that looks a little funny. We have 1/2 water. The reason we want a 1/2 water is we want 1 mole of each of our products. So now we're going to see some 1/2s occasionally when we cut our reactions down to get 1 mole of product, because we want to make sure our combustions are per 1 mole of product. Now we also have methane burning in oxygen to make CO2 and water. And we have the enthalpy of combustion of this. Well, now this might look crazy, and you wonder, well, how can you combine these to get that reaction of, again, carbon reacting with hydrogen to make methane? Now, how is that possible? Well, notice we have each of these individual substances in these chemical reactions. Methane is here, right? Hydrogen is here, and carbon is here. So what we have to do is add these chemical reactions together to get this overall chemical reaction. Well, notice one thing we'll have to do. Notice carbon and hydrogen are both reactants in this process. Here, carbon and hydrogen. So we're going to leave carbon and hydrogen there, and we're going to leave these values as is. What I do have to do, though, is this last reaction, I'm going to have to flip it around because methane is our product. So methane has to be on the other side of the reaction. If I flip this reaction around, well, then I have to flip the sign on the enthalpy of combustion as well. So we can flip these reactions around, but we have to flip their values. We can also double values. So if I needed, say, 2 hydrogens, which I do, right? I will need 2 hydrogens to make this a balanced reaction. Well, then I have to double this, put a 2 in front, and that's okay, as long as I double the amount of heat as well. So let's look at the solution for it. So here we have the overall chemical reaction that we had to flip, our CO2 plus water to get methane on the other side. Notice we flipped the energy value. So step 1 here, and we also had to do this. We had to multiply, just like I said, our hydrogen by 2, and we had to multiply that whole reaction by 2. Notice the 1/2 is gone, and so we had to multiply the heat of combustion by 2 as well. So we can multiply, flip those chemical reactions as long as we carry those values through the whole process. So we end up with this. We end up with carbon, again, on the reactant side, hydrogen on the reactant side, so we get them in our final reaction. We flipped this reaction to get methane on our product side, so it's here. Because we flipped it, we had to flip our energy value, and it looks like they forgot to flip the sign here, but we would flip the sign. That should be positive. Notice we did put the 2 in front to double this value. If we look at the sums of these, though, the answer is correct. So I apologize that even though they forgot, again, to change the sign there, again, that should be positive because we flipped this reaction. Our answer still comes out. Now, let's look at the other thing that they did, because we haven't talked about that part yet. The other thing they did here, the other thing they did is this. Notice when we add these reactions together, not only are we adding the energy values, and remember that this is a positive 890, not only are they adding the energy values, but they're adding the equations. So let's see what happens there. The CO2 on the reactant side here cancels with the CO2 on the other side. Notice all of those things are on the other side of our reaction arrow. So if I have 1 CO2 on this side, it can cancel out with 1 CO2 on this side. There's 2 oxygens over here, right? So we have to find 2 oxygens to cancel. There's 1 in this reaction and 1 here. That gives us our 2 moles of oxygen that have to cancel out. We have 2 moles of water here, 2 moles of water here. Those cancel out. And it seems kind of magical, right? But that gives us our overall reaction. Carbon plus 2 moles of hydrogen equal 1 mole of methane, and then the sum of the energies as well. Now, that is how we'll normally solve those, because we have to see how those equations fit together and if we need to multiply or flip any. Mathematically, what it's saying is that the change in enthalpy for that overall reaction is just the sum of the enthalpy changes of all the products times the moles of the products minus the sum of the enthalpy changes of all the reactants times the moles of all the reactants. That is essentially what we are doing in that last reaction. So one more example here. So now we have nitrogen monoxide reacting with oxygen gas to making nitrogen dioxide, and we want to see if we can find some reactions that fit together to solve what the overall enthalpy change is. So here are some of the reactions that they have. They have the molar formations, and sorry, some of the formatting didn't come out here. The molar changes of enthalpy of nitrogen monoxide coming from its individual gases. And again, notice they changed it per mole, so we have a enthalpy change of formation per mole. We can also find the same thing for nitrogen dioxide. And I apologize that this value didn't come up, but this value should be a plus, let's see, 33.2 kilojoules is the enthalpy change of formation for our nitrogen dioxide. So we have our two values. We need to put these equations together to get our overall reaction. We'll notice some things that we'll have to do. We want NO2 on the product side. It is already in this reaction on the product side, so I'm going to leave that reaction in place. Notice, however, I want nitrogen monoxide in my reactants. So this reaction will have to flip, meaning we'll have to flip this value to -90. Now, if we flip that, it does look like our nitrogens will cancel and our right amount of oxygens, but let's take a look at that overall solution. Okay, so here they're saying that what we are doing is we did have to flip this reaction. And now when we add them up, notice, and again, these are our reaction arrows here and here. So our nitrogen canceled out. We had 1/2 and 1/2. Notice we had 1/2 oxygen here. Well, what it's going to do is going to cancel with 1/2 of an oxygen here. So that gives us that 1/2 oxygen left. Our nitrogen monoxide comes down, our nitrogen dioxide, and notice we had to flip this value. Now it's a negative value. So when we sum them up, we have an overall negative enthalpy change, which again, negative enthalpy changes are exothermic. So this reaction will give off energy. So let's do one more Hess's law and see if we can put these together. What it wants here is the enthalpy of formation of carbon reacting with hydrogen gas to form this pentane compound. Now what it has is it doesn't have all these individual reactions, but it has a lot of heats of combustion and heats of formation. So if a heat of combustion of burning that compound, we have hydrogen reacting with oxygen gas, which is a heat of formation. Also, I guess you could think of it as a heat of combustion as well, and carbon reacting with oxygen gas, which they have listed as a heat of formation. But again, also would be a heat of combustion because we are burning that. So it says, how can we add these up to get this overall reaction? Well, if you notice a few things, this is a product, so I will have to flip this reaction around. That means I'm going to have to flip this to a positive value. I want my water where I don't know yet, but I do want my hydrogen on the reactant side, so I'm going to leave that in that place. I want carbon on my reactant side, so I'm going to leave that in that place. But notice these values are very big to get them to cancel out. Notice I need 5 carbons, so I'm going to multiply this first one by 5, the whole reaction, right? So 5 carbons, 5 oxygens, 5 CO2. Hydrogen, I want 6, so I need, and again 5 by the energy as well. I need 6 hydrogens, what will end up being 3 oxygens, and 6 waters, and again a 6 in front of this value as well. So some big values we're looking with, but let's look how it all cancels out. In the end, if we do that, notice we multiplied everything through by 5, we end up having 5 oxygens here, 8 in our final reaction, 3 here, so we have a total of 8 on the reactant side, 8 on the product side. Those cancel. Our 6 waters and 6 waters cancel because they're on opposite sides of the reaction arrow. Our carbon dioxide cancels with the carbon dioxide, and we have our overall reaction. The sums of the energies, again, we had to flip this energy, multiply this by 6, this by 5, but we find out that the enthalpy of formation of this compound overall is exothermic. Thank you.